young innovators. Our Earth spins, right? And we know the time it takes for it to do so, and it's 24 hours. But what about the sun? Have you ever looked up at the sun and wondered, does it also spin? It may seem still, but the sun is constantly turning, and today we are going to measure how fast does the sun spin. So let's take a closer look at our nearest star. Not just as a bright light in the sky, but as a dynamic, spinning sphere of plasma. The sun isn't a solid object, right? It's massive, glowing ball of gas, mostly hydrogen and helium. And it is heated to such extreme temperatures that atoms split apart. So electrons, they float freely from their nuclei in a state we call plasma. Now let's rewind back to the year 1612. A curious scientist named Galileo Galilei pointed a telescope at the sun. Not directly, of course, so he knew better. Instead, he cleverly projected the image onto a screen. And what he saw? He saw dark blotches scattered across the sun's face, sunspots. In Galileo's time, many believed that the sun was a flawless, unchanging sphere. But these mysterious spots told a different story. So day after day, Galileo tracked their motion, and what he discovered was groundbreaking. The sun actually rotates. But here's where it gets interesting. You see, solid objects like the Earth rotate as one, right? So every point on our planet takes exactly 24 hours to spin once. And that is called a rigid rotation. But the sun, it's a different story because it's made of plasma, a non-rigid material. So different parts of the sun, they rotate at different speeds. So scientists call this a differential rotation. So, how can we measure the rotation of the sun without a telescope? Now let's explore a simple method using real satellite images and some basic math. Now, what you have here is a collection of daily images of the sun, preferably over a period of 25 to 30 days. So these images, they are captured by NASA's Solar Dynamics Observatory, and what they reveal are sunspots. Here comes the first part of the activity, measuring the sunspot speed. Now, taking a prominent sunspot as it moves across the sun's face near the center, measure the distance d the sunspot traveled between the two images. Now we can find the elapsed time in hours. So assuming that the sunspots move at a constant speed on the surface of the sun, their instantaneous speed at any instant in time is equal to their average speed. So we can then simply apply the equation of the average speed between two images. Using that, we can calculate the speed v, which is given as v equal to d by t. In the next part of the activity, we are going to estimate the path length of the sunspot. So here we sketch the sunspot's path, and we take both the front view and the top view, and this is how it will be. From here, we draw the diameter d of the trajectory on the front and the top views. From here, we measure the diameter d in centimeters of the sunspot's circular path. And how can this measurement be used to compute the length of the trajectory L? So we use this perimeter diameter relationship for a circle, which is given as L equals pi d. From here, we calculate the trajectory length L. Now, having performed the part A, which is measuring the sunspot speed, which is given as V, and performing part B of the activity, which is estimating the path length, L, can we tell about the revolution period of the sunspot? So, the revolution period of the sunspot will be equivalent to the rotation period T of the sun. We can find out what the rotation period is using the results from the previous calculations. We can measure the rotation period T, which is given as L by V. And after we do this, we get the answer of rotation period in terms of hours. And to convert that into days, we can do a simple calculation, which is T by 24, which will give us the rotation period in days. And there you have it. Based on our sunspot tracking, we estimate the sun's rotation period at the equator. Tell us in the comments below, what was your answer? What was the period of rotation? It's amazing how just a few measurements can reveal the rhythm of our nearest star. So try it for yourself and see what your sun reveals. So, with a few solar images and simple measurements, we have unlocked a very powerful insight. The sun does spin, and not all paths rotate at the same speed. So this activity shows how much we can learn just by observing and thinking critically, just like Galileo did over 400 years ago. Keep exploring, the universe is full of motion and mystery. Thank you for watching.